One of the most astonishing features of the nervous system is its incredible plasticity. Our brains are remarkably adaptable, allowing us to modify our behavior to adapt rapidly to our current circumstances or based on our past experience. My name is Vanessa Ruta, and I'm a neuroscientist. I had a kind of non-linear entry into science. I come from a family of artists, and I never even considered being a scientist when I was young. My goal was actually to be a classical ballet dancer. After several years, I realized that life was probably not sustainable, at least for me, and I decided to go back to school. My lab is very interested in the interplay between instinct and learning, the sort of classic dichotomy of nature versus nurture. Instinctive behaviors, innate behaviors, are basically pre-programmed. But of course, in the complex and completely dynamic world that we live in, most behaviors have to be flexible and adaptive. And so learned behaviors really allow us to rapidly modify our behavior on a much more moment-to-moment time scale even, or over the course of our lifetime. So we do this, but actually in a very simple model system, the fruit fly Drosophila. But we can actually look at the same neuron in different Drosophila and really start to think about the computations that an individual neuron performs within this nervous system. The mushroom body is a center in the fly brain that underlies olfactory learning, allowing flies to endow meaning to any odor that they may encounter. What this means is that flies, just like humans, if they encounter an odor, for example, that is closely followed by a reward, like a little droplet of sugar, flies will learn to associate the odor with the reward. The same odor stimulus can actually drive even opposing behavioral responses. It can become attractive under one circumstance when it's paired with a reward, or aversive to the fly if it's paired with a punishing stimulus. To gain insight into the learning process within the mushroom body, we devised imaging methods that would allow us to visualize individual synaptic connections between neurons within this brain center and how they changed as a fly learns an association. One thing we discovered from this process is really how finely tuned synaptic plasticity mechanisms are within this brain center. That individual synaptic connections between neurons could be made stronger or weaker simply depending on the timing of the odor and the reinforcement stimulus, the sugar reward. This work matters because we are able to gain detailed mechanistic insight into how neural circuits can change through learning and experience or over the context of evolution to allow us to adapt to the complex and changing world around us.